Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with Venusian volcanism, the hellish beauty of our sister planet. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. This region is characterized by a complex geological history, shaped by volcanic activity and tectonic processes. Its surface is dominated by extensive plains, large volcanic structures, and thousands of volcanoes, some of which exhibit signs of recent activity. Thick clouds of sulfuric acid envelop the planet, creating a dense atmosphere that traps heat and contributes to surface temperatures exceeding 470 degrees Celsius. The geological features reveal a young surface, suggesting a relatively recent resurfacing event, likely due to widespread volcanic activity. These volcanic formations are diverse, including shield volcanoes, large lava domes, and vast volcanic plains, indicating a dynamic geological environment. The presence of large highland regions, such as Istar Terra and Aphrodite Terra, suggests tectonic forces at play, shaping the landscape through uplift and deformation. Data from spacecraft missions have illuminated the presence of volcanic pits and lava flows, hinting at ongoing geological processes. This continuous activity raises questions about the planet's geological evolution and its potential for hosting unique conditions. The high atmospheric pressure, coupled with the intense greenhouse effect, creates an environment unlike any other in the solar system. Understanding these geological aspects provides insight into not only Venus itself, but also the broader mechanisms that govern terrestrial planet formation and evolution. The significance of studying Venusian volcanism extends beyond mere curiosity about a neighboring planet. This region serves as a living laboratory, revealing critical information about planetary processes that might have parallels on Earth. Volcanic activity on Venus contributes to a better understanding of atmospheric dynamics, particularly the interactions between volcanic gases and climate. These interactions can illuminate how greenhouse gas emissions affect planetary temperatures and weather patterns over extended periods. Investigating the various types of volcanic features, such as large shield volcanoes and volcanic plains, enables scientists to reconstruct the planet's geological history. These formations suggest a complex relationship between tectonics and volcanism, providing clues about the internal structure and thermal state of Venus. Each fissure and lava flow contributes a piece to the puzzle of how heat escapes from the planet's interior. The study of Venusian volcanism also informs our understanding of exoplanets. Insights gained from the processes on this hostile world can be extrapolated to analyze the atmospheres and geological activity of distant, rocky planets. Recognizing the similarities and differences enhances knowledge about the potential for life and habitability elsewhere in the universe. The data collected from missions and observations continues to deepen the scientific community's appreciation for the intricate and often enigmatic nature of planetary evolutions. The exploration of Venus began in the early 1960s, marked by a series of ambitious missions that sought to unveil the mysteries of this neighboring world. The Soviet Union's Venera program was pioneering, sending a fleet of spacecraft to gather information. These missions revealed a harsh environment dominated by thick clouds of sulfuric acid and an atmospheric pressure nearly 90 times that of Earth's. Such conditions posed significant challenges, yet they yielded invaluable data about surface temperatures reaching an average of around 470 degrees Celsius. The United States entered the exploration arena with the Mariner program in the early 1970s. Mariner 10's flyby provided crucial insights into the planet's rotation and surface features. Subsequent missions, including Magellan in the late 1980s, employed synthetic aperture radar to map nearly the entire surface, revealing the presence of vast volcanic plains and hundreds of volcanoes, some possibly active. In the decades that followed, interest in Venus waned, overshadowed by more prominent explorations of Mars and outer planets. Nevertheless, the scientific community remained intrigued by the geological processes shaping its surface. This ongoing curiosity laid the groundwork for future missions, which aim to clarify the planet's history, climate dynamics, and potential for volcanic activity, enriching our understanding of terrestrial planet evolution. The unique composition of Venus's atmosphere plays a critical role in shaping its environmental conditions. Dominated by carbon dioxide, it constitutes approximately 97% of the entire atmospheric makeup. This dense layer creates a runaway greenhouse effect, trapping heat and elevating surface temperatures to extreme levels, often exceeding 800 degrees Fahrenheit. The presence of sulfuric acid clouds adds a harsh quality to the atmosphere, contributing to the overall corrosive environment. Trace amounts of water vapor, nitrogen, and other gases exist, indicating complex chemical processes at work. The atmospheric pressure at the surface is approximately 90 times that of Earth, creating an environment that challenges our understanding of habitability. This immense pressure, coupled with the high temperatures, renders any potential exploration difficult. Yet it also piques scientific interest. In this region, the clouds reflect sunlight, giving Venus its characteristic bright appearance from afar. Yet, beneath this thick veil lies a hostile landscape shaped by volcanic activity and vast plains. Surface features reveal signs of past geological processes, hinting at a dynamic history. The interaction between the atmosphere and surface conditions remains a focal point, as scientists seek to uncover the implications for planetary evolution and the potential for understanding similar processes on exoplanets beyond our solar system. Surface temperatures on Venus consistently hover around 460 degrees Celsius, a result of a runaway greenhouse effect that traps solar energy. This intense heat transforms the landscape into a hostile environment where molten rock can flow freely, reshaping the surface. The pressure at the surface, approximately 91 times that of Earth, exerts a crushing force, equivalent to being nearly 1 kilometer beneath the ocean's surface. Such extreme conditions create a unique geological setting where volcanic activity is likely commonplace. These parameters dictate the chemistry of Venus's surface, leading to the formation of unique minerals and compounds. Sulfuric acid clouds form high above, while the surface is primarily composed of basalt, suggesting a history of extensive volcanic processes. The harsh environment limits the presence of water in liquid form, further altering the geological dynamics of this planet. Instruments designed to withstand these conditions reveal that even in the face of such extremes, this world has retained significant geological activity. Features resembling volcanic structures, such as large shield volcanoes and extensive lava plains, indicate a dynamic interior. Understanding these surface conditions is crucial, as they offer insights into the evolutionary path of terrestrial planets and inform the search for habitable worlds beyond the confines of our solar system. The sulfuric acid clouds enveloping this region of Venus play a pivotal role in its weather dynamics. Composed predominantly of sulfuric acid droplets, they create a thick and reflective layer in the atmosphere, significantly influencing temperature regulation and solar radiation absorption. This dense concentration of clouds results in a greenhouse effect, trapping heat and maintaining surface temperatures that average around 470 degrees Celsius. These clouds not only contribute to the extreme thermal conditions, but also impact wind patterns and atmospheric circulation. High-altitude winds can reach speeds of up to 300 kilometers per hour, creating a complex system of superrotation distinct from the planet's slower rotation period. This phenomenon results in atmospheric conditions that differ dramatically from those found on Earth, fostering unique weather systems. Precipitation, while consisting primarily of sulfuric acid, does not reach the surface. Instead, it evaporates in the intense heat before making contact, contributing to the planet's aridity despite the presence of abundant atmospheric moisture. The interaction of these clouds with volcanic activity is also notable, as eruptions can inject gases and particulates into the atmosphere, altering the chemical composition and leading to potential changes in cloud formation. This intricate relationship between clouds and surface processes speaks volumes about the geological and atmospheric history of Venus. Innovative methods of remote sensing have revolutionized the exploration of Venus, enabling scientists to gather extensive data without direct contact. These techniques employ a combination of radar imaging and spectroscopy to penetrate the dense atmosphere. Synthetic aperture radar, for instance, can map surface features with remarkable precision, revealing the planet's mountainous terrains and vast plains. Infrared spectroscopy provides insights into the atmospheric composition, identifying key gases such as carbon dioxide and sulfur dioxide. This data aids in understanding the chemical processes that drive the planet's extreme conditions. By utilizing these advanced instruments, researchers have detected signs of volcanic activity and potentially active geological processes, indicating that Venus is a dynamic world. The use of spacecraft equipped with these remote sensing tools has yielded significant findings. For example, the Magellan mission, launched in the late 1980s, delivered high-resolution images of the surface, uncovering features such as large shield volcanoes and vast lava plains. Current missions continue this trend, focusing on the emission of heat from the surface and the behavior of atmospheric phenomena. This ongoing research provides a deeper comprehension of Venus's geological evolution, revealing the planet as not merely a static environment, but one shaped by its tumultuous history and ongoing processes. The complex surface of Venus showcases a variety of geological features that reflect its dynamic nature. Vast plains, often characterized by volcanic activity, dominate the landscape, indicating a history of widespread lava flows. These extensive regions, known as the lowland plains, are interspersed with numerous volcanic structures. Shield volcanoes, resembling those found on Earth, punctuate the terrain, their broad, gently sloping profiles hinting at the fluidity of past eruptions. In contrast, the highland areas present a rugged visage. Mountain ranges, such as Maxwell Montes, rise steeply, their peaks shrouded in dense clouds of sulfuric acid. These formations suggest tectonic processes that have reshaped the crust over millions of years, raising questions about the planet's internal dynamics. Impact craters, varying in size and depth, dot the surface, remnants of celestial encounters that have occurred throughout its existence. Extensive fault systems crisscross the landscape, illustrating the stresses and strains acting upon the crust. The presence of tectonic features indicates movement beneath the surface, a phenomenon that aligns with the concept of a geologically active world. This environment, marked by extreme temperatures and pressure, presents a unique study of planetary evolution, offering insights into the mechanisms that govern terrestrial bodies across the cosmos. The role of tectonics in Venusian volcanism reveals a complex interplay between geological processes and surface manifestations. Tectonic activity on this planet appears to be influenced by its thick atmosphere and high surface temperatures, which alter the behavior of its lithosphere. Unlike Earth, where plate tectonics facilitates the movement and recycling of the crust, this region exhibits a different mechanism. Evidence suggests that the crust on Venus may be rigid yet mobile, characterized by a series of faults and fractures that hint at its dynamic nature. Volcanic activity occurs in response to the buildup of pressure beneath the surface. Hot mantle plumes likely contribute to the formation of large volcanic constructs, while localized hotspot volcanism generates smaller features. The resurfacing events are believed to be episodic, leading to significant alterations in the planet's landscape over millions of years. Many volcanic structures, such as the large shield volcanoes, indicate that lava flows are extensive and can cover vast areas. This geological environment is further complicated by the presence of extensive lava plains and unique features like coronae, which suggest a history of intense volcanic and tectonic activity. The absence of significant impact craters indicates a relatively young surface, reinforcing the notion that tectonic processes are actively reshaping Venus, presenting a stark contrast to the geological histories of other rocky planets. Shield volcanoes dominate the landscape, characterized by their broad, gentle slopes. These formations arise from the eruption of low-viscosity lava, which flows easily over vast distances. Their extensive coverage suggests that Venus has experienced extensive volcanic activity over geological time, with many of these structures reaching heights comparable to some of Earth's tallest mountains. In addition to shield volcanoes of consounds, the presence of large volcanic domes reveals a variety of eruptive styles. These domes, formed by the slow extrusion of more viscous lava, exhibit steeper slopes and often result in a more localized accumulation of material. Their sizes and shapes indicate differing eruptive histories and magma compositions across the planet. Some regions feature vast volcanic plains formed from repeated lava flows that blanket the landscape. These expanses highlight the planet's capacity for sustained volcanic activity, as well as the potential for widespread resurfacing events. Additionally, the presence of volcanic pits and fissures suggests that the subsurface might still hold molten material, providing evidence of ongoing geological processes. This activity implies a dynamic interior, which contrasts with the cold, inert nature of other celestial bodies within the inner solar system. The interplay of these various volcanic features paints a complex picture of Venus's geological evolution, inviting continued study and exploration. Shield volcanoes dominate the landscape of Venus, characterized by their broad, gently sloping profiles. These formations arise from the eruption of low-viscosity basaltic lava, allowing it to flow across vast distances before solidifying. This process results in the wide, shield-like shape, distinct from the steeper profiles of other volcanic structures. Numerous examples can be found across the planet's surface. Mont Mons, one of the largest shield volcanoes, towers nearly 8 kilometers above the surrounding plains, its expansive base stretching over 400 kilometers in diameter. The gentle slopes of Mount Mons reveal a history of prolific lava flow activity, indicating a prolonged period of volcanism that has shaped its current form. Another significant example is Sapus Mons, which exhibits similar features with a diameter of approximately 450 kilometers. Its broad, shield-like structure suggests an extensive eruptive history, with lava flows that have covered the surrounding landscape. The study of these volcanoes provides insight into the thermal and tectonic processes shaping Venus. The lack of plate tectonics on this planet results in a unique volcanic activity where the mantle's heat is believed to be released through these shield structures. Observations continue to uncover the fundamental aspects of Venusian volcanism, contributing to a deeper understanding of its geological past. Stratovolcanoes on Venus exhibit distinct characteristics that set them apart from their terrestrial counterparts. These towering formations rise prominently from the surface, often reaching heights of several kilometers. Composed of alternating layers of lava flows, ash, and other volcanic debris, they embody the explosive potential of Venusian geological activity. The presence of extensive lava flows surrounding these structures suggests a history of both explosive and effusive eruptions, hinting at a complex interplay of volcanic processes. Distributions of stratovolcanoes reveal intriguing patterns across the planet's surface, concentrated mainly in regions such as Phoebe region and Atalanta Planitia. These structures hint at ancient tectonic activity that has shaped their locations. The alignment of these volcanoes may indicate a response to underlying mantle dynamics, suggesting that they are not merely isolated features, but integral components of a larger geological framework. Some formations exhibit unique features, such as broad calderas, which suggest significant volcanic collapse after explosive eruptions. Many of these calderas display evidence of subsequent lava flows, indicating ongoing volcanic activity. Meanwhile, the presence of certain radar-bright materials surrounding these volcanoes offers insight into the composition of their products, revealing variations in mineralogy that may point toward the prevailing environmental conditions at the time of their formation. Lava domes emerge as prominent features across the surface, characterized by their steep slopes and dome-like shapes, formed by the slow accumulation of viscous lava. These structures can vary significantly in size, ranging from modest hills to massive formations towering hundreds of meters high. Their formation is a direct result of the unique volcanic processes operating within Venus's thick atmosphere and high surface pressure. The significance of these lava domes extends beyond mere geological curiosity. They serve as indicators of the planet's volcanic history and activity. The presence of multiple overlapping domes suggests a dynamic environment where successive eruptions and lava flows have occurred over extended periods. This layering provides a chronological record, allowing scientists to infer the temporal evolution of volcanic activity. In this region, the composition of the lava contributes to the characteristics of the domes. The high silica content often results in a more viscous lava, which distinguishes Venusian domes from those found on other planetary bodies. This viscosity leads to their characteristic steep profiles, amido behind phosphorix danaith throtheth, as the lava does not flow far from the vent before solidifying. Observing these formations through radar and infrared imaging, researchers gain further understanding of the processes that shaped Venus's landscape, contributing to the broader knowledge of planetary volcanism and its implications for planetary atmospheres. Lava flows play a crucial role in sculpting the surface of this planet, As they emerge from volcanic vents, they create extensive fields of solidified rock, often resembling vast, undulating plains. The composition and temperature of the lava dictate both its flow characteristics and the resulting geological features. High-temperature flows can travel considerable distances before cooling, while lower-temperature eruptions tend to form more localized deposits. Evidence suggests that these flows can interact with the atmosphere in significant ways, releasing gases that contribute to the thick, sulfuric acid-laden clouds enveloping Venus. The interplay between the solid and gaseous components of this environment enhances understanding of greenhouse gas dynamics on a planetary scale. In some regions, the surface exhibits structures indicative of ancient lava lakes, providing clues about the thermal history and volcanic activity over eons. These formations may indicate periods of intense volcanism, followed by long dormancy. The continual reshaping of the landscape by lava flows creates a record of geological processes that can be analyzed to infer the planet's evolution. Given the extreme conditions on Venus, studying these lava flows offers insights not only into its past, but also into potential similarities with other celestial bodies, including Earth. The examination of these volcanic processes enriches our comprehension of terrestrial atmospheres and the factors influencing planetary habitability. Volcanic plains on Venus reveal a landscape shaped by extensive lava flows and a complex interplay of geological forces. The smooth, expansive regions, often characterized by vast and uniform surfaces, primarily consist of basaltic rock. These formations are the result of repeated eruptions that have released fluid lava, allowing it to travel great distances before solidifying. The composition of the lava, rich in iron and magnesium, contributes to the planet's distinctive yellowish hue when observed from space. Formation mechanisms of these plains are tied to the planet's unique geological conditions. Unlike Earth, where tectonic activity leads to the recycling of crustal material, Venus exhibits a more stagnant surface with minimal plate tectonics. Instead, volcanic activity occurs in localized hotspots, where plumes of molten rock rise from deep within the mantle. The absence of significant tectonic movement allows for the accumulation of large volumes of lava over time, resulting in the expansive plains that dominate the landscape. In some regions, volcanic features such as rift valleys and shield volcanoes provide insight into the processes that have shaped this environment. These formations are indicative of the planet's volcanic history and illustrate the evolutionary trajectory of its surface. Studying these plains enhances understanding of not only Venusian geology, but also the broader implications for planetary formation and evolution throughout the solar system. The surface albedo of Venus is profoundly influenced by its volcanic activity. This phenomenon shapes the planet's ability to reflect sunlight, contributing to its distinctively bright appearance in the night sky. Volcanism introduces various materials to the surface, altering the texture and composition of the landscape, which in turn affects the reflectivity. Basaltic flows, formed by lava eruptions, exhibit low albedo, absorbing significant solar radiation. Conversely, the presence of volcanic ash and aerosols can create a more reflective surface, complicating the overall albedo measurements. The interplay of these materials leads to a patchwork of albedo variations across the planet. Regions dominated by fresh volcanic deposits tend to display lower reflectivity, while areas with older, weathered lava flow may appear brighter due to the accumulation of reflective materials over time. The thermal history of this region is intricately linked to these albedo changes, impacting atmospheric dynamics and circulation patterns. Volcanism, may also influence the greenhouse effect on Venus. As gases are released during eruptions, they contribute to the thick, cloud-laden atmosphere, enhancing the planet's heat retention. This relationship between surface composition, volcanic activity, and atmospheric conditions remains a critical area of study. Understanding these interactions provides deeper insight into the geological processes that govern not only Venus, but also similar rocky bodies throughout the universe. The rotation period of Venus, lasting approximately 243 Earth days, significantly influences its volcanic activity. This slow rotation leads to unique atmospheric conditions that affect temperature distribution and, subsequently, the behavior of volcanic features. The thick carbon dioxide-rich atmosphere traps heat, creating surface temperatures that soar to around 460 degrees Celsius, fostering a dynamic yet static environment. In these conditions, volcanic eruptions may be prolonged, allowing lava flows to spread across vast expanses with minimal interruption. The heat and pressure built within the planet's crust can result in infrequent but potentially massive eruptions. These events can reshape the landscape, covering extensive areas with fresh basaltic material. Observations suggest that some regions may exhibit signs of relatively young volcanic activity, indicating that the planet's geological processes continue to evolve. The interaction between slow rotation and atmospheric dynamics also leads to a unique phenomenon known as superrotation, where the atmosphere moves much faster than the planet itself. This can influence the transport of volcanic gases, such as sulfur dioxide, which contribute to the planet's thick, toxic clouds. The resulting interactions create a complex feedback system, revealing how rotational dynamics can modulate volcanic behavior and atmospheric evolution on a planetary scale. Through this understanding, parallels can be drawn to similar processes occurring on other celestial bodies. Heat flow measurements on Venus reveal a planet shaped by intense thermal activity. Elevated temperatures near the surface suggest an active geological environment. This region exhibits a distinct distribution of heat, indicating persistent volcanic processes. The data collected from various missions have highlighted surface temperatures averaging approximately 470 degrees Celsius. These extreme conditions contribute to the planet's dense atmosphere, rich in carbon dioxide, creating a runaway greenhouse effect. Thermal emissions suggest that some areas may be experiencing significant volcanic activity. Regions with elevated heat flow hint at the presence of recent lava flows, allowing scientists to infer the potential for ongoing volcanism. The implications of these findings extend beyond Venus, offering insights into planetary evolution. Understanding heat flow patterns aids in predicting the thermal dynamics of other rocky planets. This information also informs models of planetary atmospheres and surface interactions. As volcanic activity influences atmospheric composition, it becomes crucial to assess how gases released during eruptions affect climate. The relationship between volcanism and atmospheric chemistry is evident when examining the thick cloud cover, which obscures the surface and complicates direct observations. Continued exploration and measurement of these thermal dynamics could unveil secrets about Venus's geological history and its potential parallels to Earth. Each discovery adds a layer to the understanding of planetary processes, emphasizing the complexity of celestial environments. Radioactive decay plays a pivotal role in the thermal dynamics of Venus's interior. This process involves the gradual breakdown of unstable isotopes, releasing heat that contributes to the planet's geological activity. Within this region, elements such as uranium, thorium, and potassium undergo decay, generating significant amounts of thermal energy. This internal heat influences the viscosity of the mantle, affecting magma movement and, consequently, volcanic activity. The warmth produced by radioactive decay, a flutige, combined with the pressure exerted by the planet's thick atmosphere, fosters conditions conducive to the formation of a molten layer beneath the crust. This hidden reservoir of magma can lead to periodic resurfacing events, where vast expanses of volcanic plains emerge. Evidence of shield volcanoes and extensive lava flows indicates that such events have occurred repeatedly throughout geological history. Geological history, in the absence of plate tectonics, the heat from radioactive sources may contribute to localized hotspots. These anomalies can create towering volcanic formations, some of which exhibit unique characteristics due to the high-pressure environment. The interactions between the cooling surface and the heated interior shape the landscape, crafting a world marked by stark contrasts. Understanding the role of radioactive decay thus unravels the intricate processes that define Venus, showcasing a planet alive with hidden complexities beneath its harsh exterior. The Venusian mantle consists primarily of silicate minerals, with significant quantities of magnesium, iron, and silicon. This layer, located beneath the crust, plays a vital role in the planet's geological activity. The composition is enriched by the presence of various compounds that contribute to its unique thermal and mechanical properties. Elevated temperatures, reaching up to 1000 degrees Celsius, drive the dynamics of this region, where convection currents circulate molten rock. These currents facilitate the movement of material, bringing heat from the deeper layers to the surface. The mantle's viscosity influences the rate of volcanic activity, allowing for the formation of extensive lava flows and unique geological structures. Regions of the mantle may experience localized melting, resulting in a range of volcanic features that dot the surface. The interaction between the mantle and the crust creates a complex feedback system. Elevated heat flow can lead to the thinning of the crust in certain areas, promoting the emergence of volcanic edifices. This interplay is crucial for understanding the long-term evolution of the planet. In addition, geophysical measurements reveal that the mantle may exhibit varying compositions in different regions, suggesting a history of heterogeneous processes. This variability further highlights the diverse geological landscape of Venus, providing insights into its dynamic and ever-changing surface. Magma generation processes on Venus reveal a complex interplay of heat and geological activity. Beneath the thick, carbon dioxide-rich atmosphere, the planet's crust experiences significant stress due to tectonic forces and extreme temperatures. Hot mantle plumes rise from the interior, indicating areas where heat is concentrated. This heat contributes to the melting of rock, forming magma that can eventually erupt onto the surface. The composition of this magma varies, influenced by the planet's unique geochemistry. Silica-rich lava flows, known for their viscous nature, contrast with the more fluid basaltic lavas produced by less viscous melts. These differences are critical for understanding volcanic activity and the evolution of the landscape. Volcanic features such as large shield volcanoes and extensive lava plains serve as evidence of these processes, demonstrating the complexity of Venusian volcanism. Tectonic activity also plays a significant role in magma generation. The absence of plate tectonics, combined with the presence of extensive faults and fractures, creates an environment where magma can accumulate at shallow depths. This accumulation can lead to localized melting, resulting in volcanic eruptions. The cyclical nature of these processes contributes to the reshaping of Venus's surface, emphasizing the planet's dynamic geological character. Insights gained from studying these phenomena enhance our understanding of not only Venus, but also the geological processes of rocky planets in general. The influence of water on volcanism reveals critical differences between rocky planets. In this region, water plays a fundamental role in altering magma dynamics. On Earth, the presence of water lowers the melting point of rocks, facilitating the generation of magma and influencing eruption styles. This interaction contributes to the diverse volcanic landscapes observed, as well as the formation of various geological features such as calderas and lava domes. In contrast, Venus possesses an extremely dry atmosphere with surface pressures that far exceed those of Earth. The absence of water vapor limits the potential for explosive volcanic activity. Volcanic eruptions on this sister planet are primarily effusive, resulting in the outpouring of lava flows that reshape the surface, creating expansive plains of solidified rock. This characteristic contributes to the smooth, youthful appearance of much of the Venusian terrain. When comparing both worlds, the role of tectonic activity becomes evident. On Earth, tectonics and hydrology are interconnected, influencing not only volcanic activity but also the broader geological evolution of the planet. In the absence of significant water, Venusian volcanism operates under different parameters, shaping a landscape marked by vast volcanic structures such as the imposing coronae, which stand as testaments to the unique geological processes at play in this arid environment. The intricate relationship between water and volcanism continues to be a focal point for ongoing research in planetary geology. Recent observations have revealed compelling evidence of volcanic activity on Venus, suggesting that it remains a geologically active world. This intriguing phenomenon is supported by high-resolution imaging and spectral analysis from orbiting spacecraft, which have identified numerous volcanic structures and signs of recent lava flows. Such findings challenge long-held assumptions about the planet's stagnant geological history. The surface of Venus displays vast plains, punctuated by vast volcanic features, including large shield volcanoes and vast lava domes. It appears that some regions exhibit changes over short timescales, indicating that volcanic eruptions may occur more frequently than previously believed. These changes can be detected through variations in surface temperature and alterations in the composition of the atmosphere, particularly in sulfur dioxide levels, which may suggest active outgassing. Certain areas, such as the Sapers Mons region, show signs of geological activity with newly formed lava deposits juxtaposed against older, more weathered terrain. Such contrasts provide a dynamic picture of the planet's surface processes. The presence of volcanic pits and fissures further emphasizes the likelihood of ongoing volcanic eruptions, adding complexity to the understanding of Venusian geology. Continued monitoring of these regions will enhance insights into the mechanisms driving volcanism on this extreme world. The implications for planetary evolution and atmospheres extend far beyond Venus, offering a broader perspective on terrestrial and exoplanetary studies. Impact events have played a crucial role in shaping the geological features of Venus. The planet's surface bears the scars of numerous collisions, with craters dotting the landscape, each a testament to its tumultuous history. These impacts have not only contributed to the physical characteristics of Venus, but have also influenced volcanic activity. The immense energy released upon impact can trigger volcanic eruptions, reshaping the terrain in an instant. Evidence suggests that when asteroids or comets collide with the surface, they can generate massive shock waves that penetrate the crust. This disturbance may lead to the melting of subsurface materials, resulting in the formation of magma. The subsequent rise of this molten rock can give birth to new volcanic structures, contributing to the planet's dynamic surface. The interplay between impact-induced melting and the existing volcanic systems creates a complex environment. The layering of lava flows and the distribution of volcanic features provide insight into the timing and frequency of these impacts. Understanding this relationship enhances knowledge of both Venusian geology and the potential for similar processes on other rocky planets. The study of these impact events adds depth to the understanding of volcanic activity, revealing how celestial dynamics can shape planetary evolution across the solar system. Geological studies indicate that the surface of Venus is relatively young, with estimates suggesting an age of approximately 300 to 500 million years. This timeline implies a significant amount of resurfacing has occurred, likely driven by extensive volcanic activity. The lack of impact craters, which are prevalent on other terrestrial bodies, supports the notion that a dynamic geological process is at play. The presence of large volcanic structures, such as shield volcanoes and vast plains of lava, further confirms this birth. These formations are characterized by their smooth, gently sloping profiles, resulting from the effusive flow of low-viscosity lava. The features suggest that eruptions may have been frequent and widespread, contributing to the continual reshaping of the landscape. In contrast, the absence of significant erosion indicates that the atmosphere plays a distinct role in Venusian geology. The dense carbon dioxide atmosphere, along with clouds of sulfuric acid, creates an environment where surface processes differ drastically from those on Earth. This unique interaction between atmosphere and geology leads to a complex, albeit harsh, surface environment. Ongoing analysis of radar and thermal imaging data reveals more about the surface's composition and its geological history. Understanding the age and evolution of these volcanic features provides insight into the planet's geological activity and its potential for hosting extreme forms of life. Volcanic gas emissions play a crucial role in shaping the atmospheric conditions of Venus. This region is characterized by a dense atmosphere, primarily composed of carbon dioxide with traces of sulfur dioxide and water vapor. These gases are released during volcanic eruptions, contributing to the planet's greenhouse effect. The high concentration of carbon dioxide traps heat, resulting in surface temperatures around 470 degrees Celsius. The presence of sulfur dioxide, a byproduct of volcanic activity, leads to the formation of clouds of sulfuric acid. These clouds reflect sunlight and contribute to the planet's characteristic yellowish appearance. The acidity of these clouds poses significant challenges for any potential exploration missions. In addition to altering temperature and pressure, volcanic gases can influence atmospheric dynamics. The release of hot gases can create localized convection currents, affecting cloud formation and weather patterns. This complex interplay of gases and atmospheric conditions underscores the dynamic nature of Venusian volcanism, Studying these emissions provides valuable data regarding the planet's geological history and ongoing processes. The variations in gas composition over time may indicate changes in volcanic activity and the potential for future eruptions. Such insights are essential for understanding not only Venus, but also the broader implications for terrestrial planets in our solar system. Volcanism plays a crucial role in shaping the atmospheric chemistry of Venus. The gases released during volcanic eruptions can significantly alter the composition of the thick, carbon dioxide-rich atmosphere. Sulfur dioxide, a common byproduct of volcanic activity, can react with water vapor to form sulfuric acid clouds, contributing to the planet's dense and corrosive cloud cover. This interaction creates a feedback loop where the atmospheric conditions influence volcanic behavior and vice versa. Observations from missions such as Magellan have revealed extensive volcanic plains and structures, indicative of both extensive recent activity and a dynamic geological history. The presence of extensive lava flows suggests that the planet might still experience eruptions. Such events would release vast amounts of gases into the atmosphere, further enriching the already complex mix of chemicals present. Gas measurements from the surface, alongside data collected from orbit, reveal a delicate equilibrium shaped by volcanic emissions and atmospheric reactions. As volcanic activity potentially increases due to tectonic movements, so too does the volatility of the atmospheric chemistry. This intricate relationship highlights how the geological processes underpinning Venus interact continuously with its atmospheric conditions, influencing climate patterns and surface processes, thus providing a window into the planet's past and potential future. Comparative volcanology reveals striking contrasts between Venus and Earth. Despite their similar sizes and compositions, the presence of enormous shield volcanoes on Venus, such as Mart Mons and Sif Mons, showcases a distinct volcanic profile. These formations, characterized by their broad bases and gentle slopes, suggest the dominance of low-viscosity lava flows. This differs considerably from Earth's stratovolcanoes, which often result from more explosive eruptions fueled by a combination of gas-rich magma and tectonic activity. Active volcanic regions on Venus exhibit unique surface features, including extensive lava plains and vast volcanic domes. The lack of plate tectonics on this planet suggests a different geological evolution, one that relies heavily on uniformitarian processes rather than the diverse tectonic interactions found on Earth. The absence of water on Venus further influences volcanic activity, leading to the creation of more effusive eruptions that contribute to the planet's thick atmosphere. Earth's diverse geological framework, shaped by the movement of tectonic plates, allows for a variety of eruption styles and volcanic landforms. The presence of water, along with atmospheric conditions, plays a crucial role in shaping volcanic behavior and surface evolution. This contrast underscores the complex interplay between environmental factors, solidifying the understanding of each planet's geophysical processes. Insights gleaned from these observations enhance knowledge of planetary evolution within the solar system. The absence of plate tectonics on Venus raises intriguing questions about its geological processes. Unlike Earth, where tectonic plates continuously reshape the surface, this region exhibits a more static configuration. Evidence suggests that the crust is predominantly rigid, with limited movement. The implications of this rigidity are profound, influencing volcanic activity and the planet's overall thermal dynamics. Surface features display extensive volcanic plains and numerous shield volcanoes, indicating a history dominated by volcanic activity. The presence of vast lava flows hints at a once dynamic mantle, capable of producing extensive volumes of magma without the recycling effects of plate tectonics. The heat generated in the interior may accumulate, leading to elevated surface temperatures and a sustained volcanic state. The thick atmosphere, rich in carbon dioxide, contributes to a runaway greenhouse effect, amplifying surface conditions. This atmospheric composition, combined with the lack of tectonic adjustment, creates a unique environment where volcanic gases remain trapped, further altering the planetary landscape. Observations reveal large volcanic structures, suggesting that hotspots may fuel surface activity. The relationship between internal heat and surface expression remains a key area of study. Understanding the geological history of Venus provides context for the evolution of terrestrial planets, highlighting the diverse pathways that shape planetary bodies across the cosmos. This concept of geologic youth on Venus reveals a landscape that appears relatively fresh, despite its age of approximately 450 million years. The surface exhibits minimal cratering, suggesting a history of resurfacing that masks older geological features. Volcanic activity, both active and dormant, plays a significant role in this renewal. Evidence supports the theory that vast lava flows have reshaped the terrain, creating expansive plains and vast volcanic edifices. Pillars of volcanic activity, such as those found in the Atla Regio and Phoebe region, display signs of relatively recent eruptions, indicating a dynamic geological process. This activity is consistent with the idea that Venus may still experience volcanic events, although their frequency remains uncertain. Lava domes and corona structures, unique to this region, illustrate the potential for ongoing tectonic movement and surface alteration. The thick atmosphere, primarily composed of carbon dioxide, traps heat, leading to surface temperatures exceeding 470 degrees Celsius. This extreme environment influences the chemical weathering processes, further contributing to the planet's geologic youthfulness. The interplay of intense heat and pressure likely fosters a continuous cycle of formation and destruction, making Venus a captivating study in planetary geology. The surface, with its diverse volcanic features, holds clues to understanding the evolution of not only Venus, but also other terrestrial bodies within the solar system. This region's global topography reveals a complex interplay of geological processes. The vast plains, interspersed with towering mountains, indicate a history marked by significant resurfacing events. These features suggest a relatively young surface, estimated to be less than 500 million years old, which contrasts sharply with the ancient terrains found on the Moon and Mars. Extensive lava flows dominate the landscape, exhibiting characteristics that imply fluidity and a degree of volcanic activity. The presence of large volcanic constructs, such as shield volcanoes, hints at hotspots that may be responsible for ongoing geological reshaping. Their gentle slopes rise prominently against the horizon, showcasing the forces that have shaped this enigmatic world. Rugged highland regions, punctuated by impact craters, provide insights into the planet's past. These craters, often eroded or partially buried, suggest that Venus has undergone significant tectonic and thermal evolution. The lack of water erosion on this surface further emphasizes the intense conditions present, where temperatures can soar to over 400 degrees Celsius. Radar mapping has unveiled the intricate features of this planet, revealing a landscape that is both alien and beautiful. It invites further exploration, promising to unlock secrets of planetary formation, atmospheric dynamics, and the potential for understanding processes that govern terrestrial planets throughout the cosmos. Convection currents in the mantle play a pivotal role in driving the geological activity of this planet. These currents, generated by the heat produced from the planet's core, create a complex system of movement within the rocky layers beneath the surface. As heated material rises, it cools and subsequently sinks back down, forming a continuous cycle. This process influences volcanic activity, contributing to the extensive resurfacing that has shaped Venus into its current state. The mantle's convective motions can lead to the development of large volcanic features, such as shield volcanoes and vast plains of basalt. They create the framework for volcanic eruptions, which may occur with little warning, reshaping the landscape in an instant. This phenomenon emphasizes the dynamic and ever-changing nature of the planet's geology. Temperature differences within the mantle are crucial for understanding volcanic events. The significant pressure and temperature conditions elevate the melting point of rocks, allowing for the formation of magma under these extreme circumstances. The interplay of heat and pressure allows for the emergence of materials that can travel to the surface, resulting in the formation of unique volcanic formations. The study of convection currents not only reveals the internal workings of Venus, but also enhances comprehension of similar processes that may occur on other rocky planets, providing insights into their evolution and geological history. Surface evolution is profoundly shaped by the relentless activity of volcanism. It modifies the landscape through the continuous deposition of lava and ash, leading to the creation of vast plains and mountainous regions. This process is characterized by the formation of large volcanic edifices, which dominate the terrain. These structures stand as silent monuments to the planet's dynamic history. The surface is marked by an array of volcanic features, including vast lava flows that stretch for hundreds of kilometers. These flows can bury previous geological formations, erasing signs of earlier conditions and altering the planet's atmospheric interactions. The heat generated by these volcanic events contributes to the greenhouse effect, perpetuating a cycle that exacerbates surface temperatures. The presence of volcanic gases, such as sulfur dioxide, influences atmospheric chemistry. This interaction plays a crucial role in the planet's weather systems and may even affect cloud formation. These processes highlight the interconnectedness of geological and atmospheric phenomena, emphasizing the complexity of Venusian evolution. Geological mapping reveals patterns that suggest periods of intense volcanic activity followed by relative calm. Such cycles imply that the planet's surface is in a constant state of renewal, reshaping itself over millions of years. This ongoing transformation offers critical clues about the evolution of planetary bodies and their atmospheres within the solar system. Mapping techniques employed to identify volcanic regions on Venus reveal the planet's complex geological history. Radar imaging, primarily from the Magellan spacecraft, has provided detailed surface maps. This technology penetrates the dense cloud cover, allowing scientists to discern variations in topography that indicate volcanic activity. These regions exhibit distinct features, such as large volcanic edifices, lava flows, and extensive plains resulting from past eruptions. The analysis reveals both active and dormant volcanoes, contributing to our understanding of ongoing geological processes. The presence of specific geological formations, such as coronae and large shield volcanoes, suggests interactions between tectonic and volcanic activity. Thermal infrared observations further enhance the identification of volcanic sites. Variations in surface temperature correlate with volcanic activity, indicating areas where recent eruptions may have occurred. Areas exhibiting high thermal emissions are prioritized for further investigation, helping to refine models of Venusian volcanism. Geological mapping also employs spectral analysis to discern differences in surface composition. This methodology identifies various minerals and compounds, suggesting the history of volcanic processes. Insights gleaned from these techniques inform hypotheses about the planet's atmosphere and the evolution of its surface structures. Theories on the origin of Venusian volcanism suggest a complex interplay between crustal dynamics and thermal processes. One prominent hypothesis posits that the planet's thick atmosphere contributes significantly to its geologic activity. The immense pressure at the surface, coupled with high temperatures, creates conditions that could facilitate the melting of subsurface rocks. This melting could lead to the formation of magma, which in turn drives volcanic eruptions. Some researchers propose that this volcanic activity is not uniform but rather episodic, influenced by the periodic release of accumulated pressure beneath the crust. This region may experience substantial tectonic forces that create fissures, allowing magma to escape and shape the landscape. In this context, the planet's surface appears to be a dynamic canvas, marked by vast lava flows and extensive volcanic plains. Geological features such as large shield volcanoes and vast lava plateaus provide tangible evidence of this activity, suggesting that Venus has experienced significant resurfacing events over its history. The presence of volcanic pits and structures reminiscent of terrestrial formations further supports the notion that it has been active relatively recently in geological terms. This ongoing investigation into Venusian volcanism not only enhances understanding of its geological past, but also raises questions about the broader implications for planetary evolution within our solar system. The role of hotspots in Venusian volcanic activity presents a crucial element in deciphering the planet's geological dynamics. These hotspots, akin to those found on Earth, are regions where plumes of molten rock rise from deep within the mantle, creating localized volcanism. Such thermal anomalies drive significant surface features, leading to vast lava flows and the formation of extensive volcanic structures. Research indicates that these hotspots may have been active for millions to billions of years, contributing to the planet's diverse landscape. The presence of large shield volcanoes, characterized by broad, gentle slopes, can be attributed to the repeated outpouring of lava from these areas. In contrast, more explosive eruptions might occur at sites where crustal tension allows for the rapid buildup of pressure. Geophysical studies reveal that hotspots on Venus can exhibit different behaviors compared to their terrestrial counterparts. The thick atmosphere and high pressures create unique conditions that influence eruption styles and lava composition. This environment may lead to the formation of unusual geological features, such as coronae, which are characterized by circular ridges and troughs. Understanding these hotspots is vital for piecing together the planet's volcanic history. It sheds light on the mechanisms that drive volcanism and how they may vary across celestial bodies, informing theories of planetary formation and evolution throughout the solar system. The morphology of Venusian volcanoes reveals a complex landscape shaped by unique geological processes. Predominantly, these structures exhibit characteristics distinct from their terrestrial counterparts. Most notably, the vast shield volcanoes dominate the surface. Their broad, gently sloping profiles indicative of low-viscosity lava flows. This region exhibits large volcanic edifices, such as Mart Mons, towering approximately 8 kilometers above the surrounding plains. Features like lava domes and extensive volcanic plains suggest a history of sustained volcanic activity. The presence of extensive rift zones, which are indicative of tectonic forces, further illustrates the interplay between volcanism and plate dynamics. Some of these volcanic formations are accompanied by extensive lava channels, which indicate the movement of molten rock across the surface. The lack of significant erosion on Venus contributes to the pristine nature of these volcanic features. allowing scientists to study them in their original state. This preservation offers insights into the timing and duration of volcanic events, as well as the potential for ongoing activity beneath the thick atmospheric veil. Observations made by orbiting spacecraft have identified numerous volcanic structures, each providing clues to the underlying mechanisms that govern volcanic processes on this extreme planet. The study of these formations contributes to a deeper understanding of volcanic phenomena across the solar system. Solar radiation significantly influences surface processes on this planet. Intense solar energy interacts with the dense atmosphere, resulting in extreme temperatures that reach approximately 460 degrees Celsius. This relentless heat alters the chemical composition of surface materials, fostering a unique weathering process. The combination of high temperatures and atmospheric pressure creates a harsh environment in which silicate rocks undergo transformation. Radiative heating contributes to the development of a thick layer of sulfuric acid clouds. This corrosive atmosphere plays a critical role in shaping the surface, as droplets of acid rain contribute to erosion and dissolution of underlying rock structures. The persistent exposure to solar radiation leads to a phenomenon known as space weathering, which affects the surface texture and mineralogy. This process alters the color and reflectivity of the terrain, making it a subject of keen interest for planetary scientists. In addition to chemical changes, solar radiation interacts with volcanic features. It influences the thermal dynamics of lava flows, affecting their cooling rates and solidification processes. These interactions create a varied landscape marked by vast plains, rugged highlands, and towering volcanoes. Understanding these effects provides insight not only into Venusian geology, but also into the potential for similar processes on other planetary bodies. The study of these interactions continues to reveal the complexities of this enigmatic world. The connection between volcanism and the climate of this region is profound. Volcanic activity significantly influences atmospheric composition, contributing to the greenhouse effect that characterizes Venus. Eruptions release vast quantities of carbon dioxide, a potent greenhouse gas, which traps heat and leads to surface temperatures reaching an average of approximately 800 degrees Fahrenheit. This extreme heat fosters a dynamic atmosphere characterized by thick clouds of sulfuric acid and a perpetually high-pressure environment. Observations indicate that even minor volcanic events can create localized disturbances. These disturbances can alter wind patterns and cloud formation, further enhancing the planet's already complex meteorology. The interaction between surface activity and atmospheric processes is crucial in understanding Venus's climate. Volcanism, therefore, is not merely a geological phenomenon. It plays a vital role in shaping the thermal and chemical characteristics of the atmosphere. The potential for ongoing geological activity raises questions about the planet's climatic stability. Recent data suggest that some regions may still experience active volcanism, hinting at a dynamic system that could be periodically refreshed. This cycle of activity contributes to the planet's status as an object of intense scientific inquiry. Each volcanic event acts as a reminder of the intricate relationships that define this hellish beauty, making Venus a subject of fascination within planetary science. Evidence suggests that this sister planet may have harbored liquid water in its distant past. Geological formations hint at ancient river valleys and possibly even oceans, leading researchers to contemplate the role of these bodies in shaping volcanic activity. The presence of water would have fundamentally altered the planet's geology, influencing tectonic movements and contributing to the development of its volcanic landscape. Interactions between water and volcanic materials could have created a variety of geological features. Hydrothermal systems might have formed, resulting in the release of gases and minerals that contributed to the volcanic processes observed today. This interaction suggests a complex interplay between hydrology and volcanism, raising questions about the climatic conditions that could have supported such an environment. In this context, the potential for past water activity on Venus also raises implications for its geological history. The cyclical nature of volcanic eruptions may have been influenced by fluctuations in water availability. These cycles could have contributed to the shaping of the surface, leading to the creation of vast lava plains, interspersed with remnants of ancient water features. Understanding these processes deepens the intrigue surrounding Venus. The potential for a wetter past paints a picture of a planet that once may have been more hospitable, contrasting starkly with its current inhospitable atmosphere. Insights into this transition illuminate the complexities of planetary evolution. High-pressure conditions on Venus significantly influence lava composition, shaping its volcanic landscape and revealing the intricacies of its geological processes. Elevated pressures, coupled with extreme temperatures, alter the crystallization of silicate minerals, leading to a unique array of volcanic rocks. Basaltic lavas, primarily formed under these conditions, exhibit high viscosity, which affects the flow dynamics and eruptive behavior observed on the surface. This region, characterized by its broad basaltic plains and extensive volcanic formations, displays a stark contrast to more familiar terrestrial environments. The elevated pressure results in the formation of minerals such as olivine and pyroxene, often rich in iron and magnesium. These minerals impart a distinct coloration to the surface, ranging from dark hues to metallic shades, creating an otherworldly appearance. Volcanic eruptions under such conditions are less explosive compared to those on Earth, favoring the effusive release of lava. This behavior contributes to the smooth, rolling terrains that dominate the planet's surface. These ruins of ancient volcanic activity hint at a once active geological past, offering clues about thermal processes that govern its atmosphere and surface interactions. Understanding the role of high-pressure conditions in lava composition provides a deeper perspective on Venus's geological activity, allowing for a more comprehensive examination of its evolution in the context of solar system dynamics. Volcanic eruptions on Venus occur under extreme conditions. The immense atmospheric pressure, approximately 90 times that of Earth, alters the behavior of molten rock, leading to unique eruption mechanisms. Magma, rich in carbon dioxide and sulfur, ascends through the thick crust, where its properties diverge from those observed in lower pressure environments. From the derived from the analysis of surface features and thermal data, the presence of vast plains, characterized by lava flows and large shield volcanoes, indicates frequent effusive eruptions rather than explosive ones. These geological formations suggest that the planet experiences a steady release of magma rather than catastrophic events typical of Earth's more volatile volcanoes. Modeling volcanic activity involves assessing the temperature gradients and the viscosity of the molten material under Venusian conditions. High temperatures and pressures produce a more fluid lava capable of flowing over extensive distances. Such behavior contributes to the planet's relatively young surface, with many regions displaying a lack of impact craters, indicative of ongoing volcanic resurfacing. Research continues to refine predictions regarding potential future eruptions. Understanding these mechanisms not only enriches knowledge of Venusian geology, but also offers insights into similarities and differences with terrestrial volcanic processes. The study of this enigmatic planet aids in unraveling broader questions about planetary evolution and the nature of volcanic activity across the solar system. Erosion processes on Venus are intricately linked to the planet's volcanic activity. The relentless heat and pressure present in this region accelerate the breakdown of surface materials. Lava flows, rich in silicate minerals, rise and spread across the landscape, creating new terrains while simultaneously altering existing ones. The high temperatures ensure that these flows remain fluid for extended periods, allowing them to carve channels and depressions. Chemical weathering plays a significant role as well. The dense atmosphere, comprised predominantly of carbon dioxide, interacts with volcanic gases. These interactions lead to the formation of sulfuric acid clouds, contributing to the erosion of surface features. This acid rain further enhances the dissolution of minerals, causing alterations to the planet's topography. The resultant landscape, shaped by both explosive and effusive volcanic events, is a testament to the dynamic processes at play. Impact craters, though less frequent, also contribute to the erosion narrative. When these craters form, they expose underlying materials to the harsh conditions of the atmosphere. Over time, the combination of heat, pressure, and chemical interactions facilitates the breakdown of exposed rock. The interplay between volcanic activity and erosion creates a continuously evolving surface, revealing the complex history of this neighboring world. Each volcanic event leaves an indelible mark, a record of the ongoing transformation that defines Venus. The geological processes shaping this planet exhibit characteristics reminiscent of subduction, a phenomenon typically associated with Earth's tectonics. Observations indicate the presence of large volcanic structures, suggestive of active mantle dynamics. These formations, characterized by extensive lava flows and broad plains, hint at a complex interplay of heat and material movement beneath the surface. This region displays a unique type of geological flow, where material may descend into the interior, akin to the subducting plates of Earth. The thermal energy generated by such interactions contributes to the planet's surface characteristics, unveiling a landscape marked by vast highland areas and extensive lowland plains. The heat-driven processes create zones of deformation, where the crust is compressed and stretched, resulting in intricate fault systems that crisscross the surface. Evidence from radar mapping reveals extensive volcanic features, including large shield volcanoes, suggesting that the planet's surface experiences cycles of volcanic activity. These cycles may be influenced by the convective currents within the mantle, which drive the movement of materials and reshape the crust over geological time. Understanding these subduction-like processes is crucial for comprehending Venus's geological history. It illustrates how this planet, though seemingly inhospitable, maintains a dynamic and evolving landscape, shaped by forces that while different from those on Earth, reflect a shared planetary narrative of change and adaptation. This dynamic landscape is further influenced by the presence of aerosols within its thick atmosphere. These microscopic particles play a critical role in regulating the thermal structure and composition of the surrounding air. Composed mainly of sulfuric acid droplets, they create a veil that scatters sunlight and contributes to the greenhouse effect. This phenomenon traps heat, elevating surface temperatures to an average of around 460 degrees Celsius, a stark reminder of the planet's intense volcanic activity. Aerosols also affect cloud formation, leading to the development of dense, reflective layers that encircle the planet. These clouds create a complex interplay of light and heat, resulting in a unique atmospheric profile. The interaction among these particles, along with the planet's rotation and varying topography, creates intricate wind patterns that influence weather systems. The winds can reach speeds of up to 300 kilometers per hour, shaping the upper atmosphere, while also impacting surface conditions. In addition to their role in climate regulation, Aerosols contribute to the chemical processes that sustain Venus's peculiar atmospheric composition through interactions with gases such as carbon dioxide and sulfur dioxide. They facilitate reactions that help maintain the planet's balance. This intricate web of interactions underscores the complexity of Venusian dynamics and the essential function of aerosols within this alien environment. Volcanism on Venus shapes not only its surface but also its atmospheric composition. Eruptions release vast quantities of sulfur dioxide and other gases, contributing to the dense cloud cover that envelops the planet. This relentless geological activity raises significant questions about the implications for habitability. The presence of active volcanoes suggests that the planet is geologically alive, continuously reshaping its environment. The interplay between volcanic gases and the atmosphere creates a harsh environment, characterized by high temperatures and pressures. The average surface temperature hovers around 460 degrees Celsius, a consequence of a runaway greenhouse effect. This extreme climate challenges the possibility of life as it exists on Earth, yet it invites contemplation of extremophiles, organisms that thrive in conditions once deemed inhospitable. Understanding Venusian volcanism provides insights into planetary processes that could inform the search for life elsewhere. The potential for volcanic activity to influence atmospheric chemistry raises intriguing possibilities about the resilience of life. If similar processes were to occur on other celestial bodies, they might foster environments where life could adapt and flourish under extreme conditions. The study of these volcanic features, such as vast lava plains and towering volcanoes, reveals a history marked by cataclysmic events, offering a glimpse into the evolution of this enigmatic planet. Each observation contributes to a broader understanding of planetary habitability across the cosmos. Theories on the future of volcanic activity on Venus suggest a complex interplay of geological processes. Current models indicate that the planet may still harbor active volcanoes, with some regions displaying signs of recent lava flows. The potential for eruptions remains a focal point of research, as scientists analyze the planet's surface for clues. This region, with its extensive lava plains and volcanic edifices, provides critical data that could unravel the mysteries surrounding its geological history. Temperature and pressure conditions, combined with a dense atmosphere rich in carbon dioxide, create a unique environment for volcanic processes. Predictions indicate that fluctuations in internal heat may trigger periodic eruptions, contributing to the ongoing evolution of the landscape. The presence of volcanic gases, such as sulfur dioxide, highlights the potential for future atmospheric interactions, altering the chemical composition of the thick clouds enveloping the planet. These phenomena may not only reshape the surface, but could also influence the long-term climate of Venus. Understanding the mechanisms driving these processes is essential for comprehending the planet's past and future. Observations from orbiting spacecraft and ground-based telescopes continue to refine these theories, revealing patterns that may indicate cycles of activity.
Thoya Fosaneklastali Jaza of this planet is marked by a series of volcanic events that have shaped its surface over millions of years. Lava flows, vast plains, and rugged highlands reflect the evolution of an environment that has undergone significant transformations. The smoothness of many regions suggests a relatively young surface, continuously repaved by volcanic activity. This resurfacing process erases older features, leading to a landscape that appears uniform and unblemished. Evidence indicates that volcanic eruptions may have occurred in both effusive and explosive forms, generating a variety of landforms.
The expansive basaltic plains are thought to result from extensive lava flows, while the presence of large volcanic structures, such as shield volcanoes, hints at the potential for more complex eruptive behavior. These formations, often towering several kilometers above the surrounding terrain, provide insight into the planet's thermal and tectonic dynamics. Geological dating techniques suggest that significant volcanic activity may have persisted into relatively recent geological time.
This ongoing process raises questions about the planet's current state of volcanism and the potential for future eruptions. Analysis of atmospheric gases, particularly sulfur dioxide, supports the idea that this region may still harbor active volcanic systems. Understanding the historical evolution of Venus's volcanic landscape is crucial for piecing together the planet's geological narrative and its comparison to Earth's dynamic processes. The interaction between volcanism and other geological processes on Venus reveals a complex web of influences shaping its surface. The planet's intense heat contributes to a unique style of volcanic activity, resulting in vast plains of basaltic lava. These formations exhibit a smooth, rolling appearance, a testament to the fluid nature of molten rock under extreme temperatures. It becomes evident that the high-pressure environment affects the composition of the lava, altering the chemistry compared to terrestrial counterparts.
Tectonic movements further complicate this landscape, as the thick lithosphere experiences stresses that can lead to rifting and buckling. These processes function in tandem with volcanic eruptions, creating features such as coronae, large, circular structures formed by upwelling magma and subsequent surface deformation. This interaction suggests a planet consistently reshaping itself through a combination of internal heat and surface pressures. Erosion, although minimal due to the dense atmosphere,
plays a role in altering the volcanic terrain over extended periods. Chemical weathering occurs, affecting the basaltic rock and leading to the development of unique mineral deposits. The atmosphere's corrosive elements further interact with volcanic materials, creating intricate surface features that speak to the ongoing evolution of this hostile environment. Each of these processes contributes to a broader understanding of the underlying dynamics at play on this enigmatic planet.
The exploration of Venusian volcanoes through orbital missions has unveiled an intricate landscape shaped by intense geological activity.
These missions, equipped with advanced imaging technologies, have provided detailed maps of the planet's surface, revealing vast plains dotted with volcanic structures. The data collected indicates that volcanism on Venus is not a relic of the past, but an ongoing process, with some regions exhibiting signs of relatively recent eruptions.
Topographic analyses highlight the presence of large shield volcanoes, their broad and gentle slopes indicative of fluid lava flows. Imaging from various missions has captured the unique characteristics of these formations, including their extensive lava channels and unique surface textures. The sheer scale of these volcanic edifices dwarfs many found on Earth, offering insight into the planet's geologic history and evolution. Thermal imaging has detected hotspots,
suggesting active volcanic processes beneath the surface. These thermal anomalies hint at the possibility of magma movement, reinforcing theories that Venus may still be geologically alive. In addition to volcanic features, the exploration of atmospheric phenomena linked to volcanism has provided a more comprehensive understanding of how gases released during eruptions might interact with the dense atmosphere.
These missions continue to reshape the scientific community's perception of Venus,
uncovering the complexities of its volcanic landscape with each passing orbit. Future missions targeting Venusian volcanism promise to deepen insights into its geological and atmospheric dynamics. Planned spacecraft aim to employ advanced imaging techniques, enabling high-resolution observations of volcanic activity and surface changes. Equipped with spectrometers, these missions will analyze gas compositions, offering data on sulfur dioxide and other volcanic gases, which play crucial roles in the planet's atmospheric chemistry.
In this region of the solar system, the potential for discovering active volcanism remains tantalizing. Recent radar imagery suggests that some volcanic structures are relatively young, indicating that eruptions may still occur. Continuous monitoring through orbiting satellites will provide real-time data, allowing scientists to establish a clearer timeline of volcanic activity and its impact on the surrounding atmosphere. Future landers will focus on selected regions exhibiting signs of recent geological activity.
By conducting in-situ analysis of surface materials, these missions will enhance the understanding of the planet's geological history and the processes that shaped it. This comprehensive approach integrates remote sensing with ground-level investigation. Collaboration among international space agencies amplifies the scientific potential of upcoming missions. The pursuit of knowledge regarding Venusian volcanism not only enriches planetary science, but may also inform broader discussions on volcanic processes across the solar system. Insights gained will illuminate the intricate relationships between geology and atmospheric conditions on this enigmatic planet.
SSS plays a critical role in unveiling the mysteries of Venus's surface. This approach involves the direct study of materials in their natural environment, allowing for a more accurate assessment of geological features and chemical compositions.
The deployment of landers capable of withstanding extreme temperatures and pressures reveals the planet's volcanic history. Instruments designed to measure elemental abundances and mineralogy provide insights into the processes that form and alter the landscape. Surface temperatures on Venus exceed 480 degrees Celsius, creating conditions that challenge even the most advanced technology. These landers often endure only a short time, yet their findings leave a lasting impact on understanding volcanic activity.
Observations indicate that many of these formations are relatively young, suggesting that volcanic processes may still be active today. Utilizing spectrometers and cameras, researchers analyze the mineral content of the rocky terrain, identifying signs of past eruptions and lava flows. The discovery of sulfuric acid clouds above the surface hints at chemical interactions between the atmosphere and the geology below. Each measurement collected offers a piece of the puzzle, gradually constructing a clearer picture of the planet's evolution. In situ analysis.
In situ analysis reveals significant challenges posed by the extreme conditions of this region. Surface temperatures on Venus soar well above 400 degrees Celsius, rendering most terrestrial instruments ineffective. The dense, corrosive atmosphere contains abundant sulfuric acid, which further complicates the viability of long-term missions. The intense pressures experienced near the surface, nearly 90 times that of Earth, create an environment hostile to both equipment and potential human exploration.
These complications necessitate innovative approaches to study volcanism. Robotic missions equipped with specialized heat-resistant materials and protective coatings are essential. The design of these instruments must account for rapid degradation, ensuring functionality during their limited operational periods. Each mission aims to collect data on volcanic activity, surface composition, and atmospheric dynamics. Yet the challenges continue to evolve. Significant geological features, such as vast lava plains and large volcanic constructs, provide critical insights into the planet's volcanic history.
Their examination can elucidate processes that have shaped this world over millions of years. The existence of active volcanism raises questions about the ongoing geological processes and their implications for the planet's atmosphere. Understanding these phenomena not only enriches our knowledge of Venus, but also sheds light on the similarities and differences with Earth,
enhancing the broader context of planetary science.
The pursuit of knowledge regarding Venus has been significantly advanced through cutting-edge technology. Instruments deployed aboard various spacecraft have provided crucial data, revealing intricate details about its atmosphere and surface. These advanced sensors detect subtle variations in temperature and pressure, offering insights into its dynamic climate systems. Recent missions have utilized synthetic aperture radar,
capable of penetrating thick clouds and mapping the planet's surface with remarkable precision. This technology has unveiled vast volcanic plains and mountainous regions, shaping a clearer picture of its geological activity. Data collected from infrared spectrometers has further elucidated the composition of atmospheric gases, indicating the presence of sulfur dioxide, a potential marker of volcanic eruptions. Robotic landers and atmospheric probes have played vital roles in the exploration narrative. These devices endure extreme conditions, transmitting data about surface temperatures exceeding 460 degrees Celsius and atmospheric pressures nearly 90 times greater than Earth's. Each mission contributes to a growing repository of knowledge, complementing the findings from previous generations of explorers. Artificial intelligence and machine learning algorithms assist scientists in analyzing vast datasets generated by these missions. They uncover patterns and anomalies that may indicate volcanic activity or atmospheric changes.
This evolving technological landscape continues to redefine our understanding of Venus, emphasizing its complexities and the intricate processes that govern its environment. The intersection of geology and astrobiology on Venus presents a fascinating arena for exploration. Surface features indicate a history marked by extensive volcanic activity, with vast plains shaped by ancient lava flows and towering mountains formed from tectonic forces. These geological processes may hold clues to the planet's past,
offering insights into its atmospheric evolution and the potential for habitability. Investigations reveal that certain areas of the surface exhibit signs of past water presence, suggesting a more temperate climate in its distant past. This observation raises questions about the planet's capacity to support life, even if only in primordial forms. The presence of minerals altered by water hints at possible biological interactions, fostering curiosity among scientists regarding the potential for extremophiles to have existed in some form.
The dense atmosphere, rich in carbon dioxide, creates extreme pressure and temperature conditions that challenge conventional life as known on Earth. Yet, kan the existence of microbial life in harsh environments on our planet encourages the hypothesis that similar organisms could adapt to the Venusian atmosphere. Instruments designed for astrobiological studies continue to analyze atmospheric composition, searching for biosignatures amidst clouds of sulfuric acid. These efforts deepen the understanding of how geological processes and life's potential are intertwined, painting a picture of a planet shaped by both chaos and possibility. The volcanic mystique of this planet has long captivated human imagination, inspiring countless myths and artistic expressions throughout history. Ancient civilizations viewed it as a representation of beauty and destruction, often personifying it as a goddess or a force of nature. Literature and art have drawn from its fiery landscape, reflecting the duality of allure and danger inherent in its volcanic features. In modern times, scientific exploration has added layers to this cultural narrative. The enigmatic clouds and surface temperatures of the planet have spurred interest in the potential for extreme life forms, fostering discussions about resilience and adaptability. This notion reverberates within the realms of philosophy and ethics. As humanity contemplates its existence in the universe, the idea that life might thrive in such hostile conditions reshapes understanding of biology and the limits of habitability. Media representations often oscillate between a romanticized view of Venus and a stark reminder of its harsh realities. Documentaries, films, and educational content frequently highlight its geological phenomena, merging science with speculative storytelling. This synthesis not only informs but also invites deeper reflection on humanity's place in the cosmos. The cultural impact of Venus, intertwined with its volcanic characteristics, continues to evolve, echoing through time and across disciplines. This connection to volcanism has inspired numerous works in popular science fiction, where the planet's extreme conditions serve as a backdrop for imaginative narratives. Writers often depict Venus as a landscape of molten rock and dense clouds, creating settings that evoke both wonder and dread. The heat and pressure present in this region become pivotal elements in these tales, shaping the experiences of characters who navigate its hostile environment. In many stories, volcanic activity is used as a metaphor for transformation, representing both destruction and rebirth. This duality reflects the planet's nature, where eruptions can reshape the surface in an instant, reminding readers of the powerful forces at play. The imagery of flowing lava and ash clouds resonates deeply, often symbolizing the uncontrollable aspects of existence. Scientific exploration, too, finds its way into these narratives. The depiction of probes and rovers braving the Venusian atmosphere highlights humanity's relentless quest for knowledge. These missions, fraught with peril, serve as a testament to resilience and ingenuity, showcasing the determination to uncover secrets hidden beneath the clouds. As the fascination with Venusian volcanism continues to thrive, the planet remains a source of inspiration, prompting further inquiry and creativity across various forms of expression. The interplay between science and imagination enriches our understanding of this enigmatic celestial neighbor. A colossal insights from other rocky planets deepen the understanding of Venusian volcanism. Mars, with its vast plains and towering shield volcanoes, provides a contrasting case study. The dormant Olympus Mons, standing nearly 25 kilometers high, showcases how volcanic activity can shape a planet's surface over eons. This immense structure, formed by repeated lava flows, highlights the differences in geological processes between the two worlds. While Venus is shrouded in a thick atmosphere that traps heat, Mars experiences extreme temperature variations, influencing the nature of its volcanism. Mercury, the innermost planet, reveals another layer of complexity. Its surface is marked by numerous impact craters and extensive lava plains, suggesting a history of volcanic activity, albeit on a smaller scale than its neighboring planets. The lack of substantial atmosphere allows for a clearer observation of its geological features. offering insights into early planetary formation and the evolution of volcanic processes. The Moon, though smaller, also contributes to this comparative analysis. Its basaltic plains formed from ancient volcanic eruptions serve as a testament to the volcanic activity that once existed. Each rocky body brings unique characteristics to the table, allowing scientists to piece together the history of planetary formation and the fundamental processes that govern their evolution. These studies collectively enhance the comprehension of the dynamic nature of rocky planets in the solar system. The impact of Venusian volcanism on space missions has been profound, shaping the objectives and technologies employed by various exploratory endeavors. Missions to this planet must contend with extreme surface conditions, including temperatures that soar above 450 degrees Celsius and pressures nearly 90 times that of Earth. These harsh realities necessitate robust engineering solutions, allowing spacecraft to withstand an environment that would quickly incapacitate lesser designs. The dense mass of local composition, rich in sulfuric acid clouds, further complicates operations, demanding specialized materials and protective coatings. Such challenges have led to innovative approaches in both lander and orbiter missions. For instance, the Magellan spacecraft, launched in 1989, utilized synthetic aperture radar to penetrate the dense atmosphere, mapping the surface and revealing vast volcanic plains and shield volcanoes. Subsequent missions have continued to unravel the complexities of this planet. The long-debated question of current volcanic activity remains at the forefront, with observations indicating potential outgassing events and surface changes. Such findings could suggest a geologically active world, prompting renewed interest in Venus as a dynamic environment. Each mission contributes invaluable data, enhancing our understanding of not only Venusian geology but the principles governing rocky planet evolution throughout the cosmos. The harsh conditions of Venus present formidable challenges for potential colonization efforts. Surface temperatures average around 480 degrees Celsius, with atmospheric pressure exceeding that of Earth by more than 90 times. Such extremes necessitate innovative engineering solutions for habitats designed to withstand relentless heat and crushing pressures. Floating cities in the upper atmosphere emerge as a theoretical alternative, where conditions are comparatively mild. Here, temperatures hover around 20 degrees Celsius, and pressure is similar to that experienced at sea level on Earth. The dense clouds of sulfuric acid and carbon dioxide offer both obstacles and opportunities. While the atmosphere is corrosive, it also contains valuable resources that could be harnessed for sustaining human life. Techniques for extracting water and producing oxygen from local materials could support future inhabitants. Scientific studies are currently exploring the feasibility of these ambitious projects. The lessons learned from Mars colonization efforts may prove instrumental, yet the unique characteristics of Venus require distinct strategies. In the quest for human presence beyond Earth, this region beckons with its extreme challenges, inviting researchers to innovate and adapt. Each exploration mission fosters a deeper understanding of the planet's environment, enhancing the prospects for venturing into this hostile yet intriguingly beautiful realm. Earth serves as a vital reference point for understanding volcanic activity on Venus. Geologically active regions on our planet offer insights into the processes that shape the surface of its sister planet. Basaltic volcanoes, similar to those found on Earth, are believed to dominate Venusian geology. This similarity suggests that the mechanisms driving volcanic eruptions may share common traits across both worlds. Thermal imaging and radar mapping reveal extensive lava flows and large volcanic structures, indicating a dynamic history of volcanic activity. Features such as large shield volcanoes hint at effusive eruptions, where lava steadily pours from the vent, gradually building up large landforms. Such formations can be observed in areas like the Hawaiian Islands, providing a terrestrial counterpart for analysis. Conversely, the potential for explosive volcanic events on Venus remains a subject of investigations. Evidence of calderas and other explosive features raises questions about the composition of the atmosphere and its interaction with the molten rock. Understanding this volatile environment relies upon comparative studies, leveraging the rich volcanic history of Earth to inform hypotheses about Venus. Geochemical analyses of terrestrial volcanic gases, particularly the presence of sulfur compounds, offer a glimpse into the atmospheric dynamics that may also exist on Venus. These parallels deepen the knowledge of volcanic processes and enhance the comprehension of planetary evolution beyond our own. The contributions of citizen scientists have become increasingly significant in the exploration of Venus. Enthusiasts from diverse backgrounds have actively engaged in data collection, analysis, and interpretation, enriching the scientific community's understanding of this enigmatic planet. In this region, amateur astronomers utilize accessible technology to capture images and observations, revealing previously unnoticed features on Venus's surface. Public participation has opened avenues for innovative research methodologies. With access to advanced software and satellite imagery, individuals can analyze volcanic activity and atmospheric phenomena, providing valuable insights that complement professional research. This collaboration has led to the identification of potential volcanic eruptions, aiding scientists in monitoring the planet's dynamic environment. Educational programs and online platforms have fostered a community of passionate individuals, allowing them to contribute meaningfully to a field traditionally dominated by experts. Through collective efforts, they have compiled databases of observations, enhancing the repository of knowledge that informs ongoing studies. The integration of citizen science into Venus research exemplifies how collective curiosity can bridge gaps in understanding. As these contributors continue to explore and document the complexities of this hellish beauty, the interplay between professional and amateur efforts promises to yield further revelations, illuminating the mysteries that linger within Venus's thick atmosphere. The future of Venusian atmospheric studies opens avenues for unprecedented discoveries. Advanced technologies, including high-resolution imaging and atmospheric probes, are set to enhance understanding of its dense cloud layers and their chemical compositions. Notably, these innovations will facilitate the examination of sulfuric acid clouds, which play a crucial role in the planet's corrosive environment. The deployment of new missions, such as orbiters and landers, will provide direct data on surface conditions, atmospheric pressure, and temperatures, enriching the current knowledge base. This region exhibits extreme climatic phenomena, including superrotational winds that travel faster than the planet's rotation. Insights into these dynamics could reshape theories of planetary atmospheres. All schists that lose meistern were for reshape theories of planetary atmospheres. Some researchers speculate that microbial life could exist within the upper cloud layers, where conditions may be less inhospitable. The prospect of finding life, even in the most unexpected environments, galvanizes scientific inquiry. Collaboration between global space agencies and research institutions is likely to accelerate progress. Joint missions could pool resources and expertise, leading to more comprehensive investigations. As Venus continues to capture the attention of scientists, the quest for knowledge will deepen, revealing the complexities of this enigmatic planet and its atmospheric processes. Each new finding will contribute to a broader understanding of planetary evolution and the conditions necessary for life. International collaboration in space exploration fosters a unique environment for scientific discovery by pooling diverse expertise and resources. Various nations can enhance their investigative efforts, particularly regarding celestial bodies like Venus. This cooperative approach leads to comprehensive missions that might otherwise be unattainable for individual countries. Through shared responsibilities, missions become more ambitious, enabling the deployment of advanced technologies and innovative methodologies. Contributions from multiple scientific communities allow for the integration of different instruments and techniques, enhancing data collection and analysis. This collaboration also facilitates the exchange of ideas, inspiring new questions about planetary phenomena. NASA scientists unite efforts. They can delve deeper into the complexities of Venusian volcanism. Collaborative missions may employ orbiters, landers, and atmospheric probes, providing a multifaceted view of its geological processes. These coordinated endeavors allow for a more detailed assessment of the planet's surface and its atmospheric dynamics, shedding light on volcanic activity and its implications for planetary evolution. The exchange of knowledge and findings among global researchers strengthens the foundation of planetary science. It encourages the development of joint initiatives, leading to more extensive educational outreach and public engagement. This united front in exploration not only enhances understanding of our neighboring planets, but also cultivates a sense of shared stewardship over the cosmos. The ethical considerations surrounding planetary exploration arise from the profound responsibility humanity carries as it ventures into these otherworldly realms. The potential for contamination, both biological and geological, looms large over missions to celestial bodies such as Venus. This region, with its harsh atmospheric conditions and volcanic activity, presents unique challenges. The fear of inadvertently altering ecosystems or mismanaging resources drives discussions on protocols and preventative measures. Attention must also be given to the implications of ownership and exploitation. As interest in mining asteroids and other planetary bodies grows, questions emerge regarding the rights to these resources. These discussions require a careful examination of international laws and agreements, ensuring that the pursuit of scientific knowledge does not lead to a new age of colonization. Additionally, the philosophical ramifications of discovering life, even in microbial form, have the potential to reshape humanity's worldview. Such findings would necessitate a re-evaluation of the ethical frameworks guiding exploration, emphasizing the need for respect and caution when engaging with extraterrestrial environments. The delicate balance between exploration and preservation underscores the importance of fostering a culture of responsibility within the scientific community. Striving for harmony between curiosity and ethical stewardship may guide. The interdisciplinary nature of Venusian volcanology encompasses a wide array of scientific fields, merging planetary geology, atmospheric science, and astrochemistry. This integration allows for a comprehensive understanding of volcanic activity and its implications for the planet's environment. Geological surveys reveal extensive lava plains, volcanic structures, and the unique characteristics of these formations, indicating a dynamic geological history. Atmospheric studies uncover the effects of volcanic gases on the thick clouds of sulfuric acid that envelop the planet. The interplay between surface activity and atmospheric composition is vital, as it influences climate dynamics and potentially habitability. These gases, primarily carbon dioxide and sulfur dioxide, contribute to a runaway greenhouse effect, raising surface temperatures to extremes. Remote sensing technology provides critical data, enabling scientists to analyze surface features from orbit. Observations from missions like Magellan have revealed vast volcanic provinces and indicative tectonic activity. This region's surface is intricately shaped by processes such as effusive and explosive volcanism, which define its hellish landscape. The phenomenon of Venusian volcanism can also extend to exoplanetary studies, offering insights into how similar processes may manifest on distant worlds. Such research fosters a deeper appreciation for the complexities of planetary evolution, highlighting the interconnectedness of various scientific disciplines in unraveling the mysteries of our celestial neighbor. The legacy of past missions reveals a wealth of information that continues to shape our understanding of Venusian volcanism. Pioneer Venus, launched in 1978, marked a significant milestone in this exploration. It provided the first detailed radar images of the planet's surface, unveiling a landscape dominated by vast volcanic plains and towering shield volcanoes. These initial observations laid the groundwork for subsequent missions, allowing scientists to identify and map numerous volcanic features. Magellan, which followed in the early 1990s, contributed further insights with its high-resolution radar mapping. It uncovered structures that suggested both active and dormant volcanic processes, hinting at a geologically young surface. This region displayed evidence of lava flows and potential venting activity, suggesting that volcanism on Venus may still occur. The European Space Agency's Venus Express, launched in 2006, enriched the narrative by studying the atmosphere and surface interaction. It provided critical data on sulfur dioxide levels, hinting at ongoing volcanic activity and its impact on atmospheric chemistry. These missions collectively underscore a significant realization. Venus is not simply a static entity, but a dynamic world shaped by volcanic forces. Each piece of data serves as a reminder of the planet's tumultuous history, prompting further inquiry into its geological and atmospheric processes. Continued exploration remains essential in exploring the enduring questions surrounding this enigmatic neighbor. Advancements in technology have become pivotal in the study of celestial bodies, including the intriguing surface of Venus. The integration of artificial intelligence and machine learning enhances our understanding of planetary science, particularly in analyzing vast datasets collected from various missions. These sophisticated algorithms can identify patterns and anomalies that might elude traditional analytical methods. Data from satellites and landers is processed to reveal geological features, atmospheric compositions, and potential volcanic activity. This region's high temperatures and pressures create significant challenges for instrumentation, making AI-driven approaches invaluable in interpreting the information gathered. Machine learning models are trained on the characteristics of known geological formations, allowing them to predict the presence of similar structures on Venus. This predictive capability aids scientists in determining the planet's volcanic history and assessing the likelihood of active eruptions. As the exploration unfolds, this technology continues to evolve, adapting to new discoveries and advancing our comprehension of this hostile environment. The interplay between AI and planetary science not only streamlines data processing, but also offers insights into the dynamics of extraterrestrial atmospheres. Each layer of information contributes to a more nuanced understanding of Venus, illuminating the complexities of its geological past and atmospheric behavior. The continued evolution of these technologies promises to redefine our approach to studying planetary systems. The future of astrobiology and Venusian studies rests upon a foundation of advanced exploration techniques and theoretical models. As researchers turn their gaze toward the thick, sulfuric clouds enveloping this sister planet, the intricate processes that govern its harsh environment become increasingly crucial to understand. This region, marked by intense atmospheric pressure and extreme temperatures, presents unique challenges that can inform the search for life beyond Earth. Ongoing investigations into the planet's geology and atmospheric chemistry reveal potential analogues for understanding exoplanets with similar hostile conditions. Insights gained from Venus may illuminate the limits of habitability and the resilience of life in extreme environments. The potential for microbial life in the upper atmosphere, where conditions are relatively milder, captivates scientists, driving innovative missions aimed at direct sampling. These initiatives harness cutting-edge technologies, including aerial drones and robust landers designed to withstand the planet's extreme conditions. The knowledge gained will not only enhance our grasp of Venus itself, but expand the horizons of astrobiology, offering a clearer picture of life's possible manifestations throughout the cosmos. Collaborative efforts among international space agencies signify a united commitment to unraveling the complexities of this planetary enigma, encouraging interdisciplinary approaches that bridge geology, atmospheric science, and biological research. The enduring mysteries of Venusian volcanism continue to challenge our understanding of planetary processes. While surface observations reveal vast lava plains and extensive volcanic structures, the precise mechanisms driving these eruptions remain elusive. Geological evidence suggests a dynamic interior, yet the details of its composition and activity are still debated. The atmosphere, thick with carbon dioxide and sulfuric acid clouds, complicates direct observation. Instruments aboard orbiters and landers have collected valuable data, yet they only hint at the complex interactions occurring beneath the surface. This region, with its extreme temperatures and pressures, presents formidable challenges for exploration. The presence of volcanic features such as large shield volcanoes and extensive lava flows indicates a history of substantial outgassing. These phenomena raise questions about the thermal state of the planet's interior. Are the currents within its mantle responsible for these eruptions? Or do they signify a deeper, more intricate cycle of geological activity? Each mission to Venus enriches the body of knowledge, revealing fragments of a story still unfolding. While some volcanic processes may mirror those observed on Earth, others diverge sharply, suggesting unique evolutionary paths. The pursuit of answers continues, driven by curiosity and the desire to comprehend our celestial neighbor, forever shrouded in mystery yet undeniably captivating.